So this item is a 2.3 item we'll be talking about today. And on this first chart here, you'll see that there is a URL for getting to a SlideShare site that will allow you to see these charts if you want to look at them with your presentation at the same time. So this first chart is just contributions, just to let you know this is a relatively large item, and I just want to take a minute to thank those, and Randy will be helping me present today, and so pretty significant effort. This chart, I'm going to talk a little bit about the agenda, because the agenda is a little bit confusing. So the first topic is some background topics, and for some of you it will be very basic, and for some of you this will be new information. I could have elected just to put the background in the backup, but I think it's important background information because I'm going to be using a lot of the terms and concepts to explain this issue, and so I think it's really important that we level set. So bear with me when I go through topic 1. And then how this topic flows is also interesting. There's actually two different issues here that will be solved by the single solution. So I'm going to describe issue number 1 and how it applies to ZVM Linux, the ZVM vSwitch environment, and then how this HiperSockets Converged Interface solution resolves that. And then I'm going to talk about another issue that's basically just ZOS only. And some of you may be interested in one topic or the other, but I think it might be interesting for you to hear both perspectives. So it's going to flow with one issue, a solution, the second issue, and how that solution. At that point in time, then I would turn it over to Randy, and Randy will take you through how ZOS COM Server implements this solution. So I'm going to be talking about system concepts, architecture, and background information. So on this chart, page 4, let's talk about something that ZOS COM Server customers are not typically, you don't typically hear this topic, and this is this notion of transport modes relative to the OSA and HiperSocket system architecture, also referred to as QDIO. We use these terms internally called Layer 2 and Layer 3 mode, and while they're very similar to networking LAN type Layer 2 architecture modes, they are slightly different because their internal aspects control different things. So basically what it really amounts to is Layer 2 basically moves packets around inside the system based on the MAC address. So in that mode, the hardware has no knowledge of the Layer 3 protocol. It simply just moves frames based on destination MAC address. You can also configure your host operating system in Layer 3 mode, and the Layer 3 modes that are supported are IPv4 and IPv6. In that case, the hardware does understand the Layer 3 mode, and it moves packets around inside the system based on destination IP address, or next hop, if you will. And so there we can also get some assist and some other help from the hardware when we're in Layer 3 mode. So now what's really important here is that the terms for this Layer 2, Layer 3 mode, this is System Z architecture relative to this discussion today. So this does not mean Layer 3 does not mean that OSA or HiperSockets behaves as an IP router. That's not true. They do switch or forward packets based on destination IP address, but they don't insert themselves as a traditional IP router. So again, this is internal processing, and the mode that's defined here is in software. And so the operating system will define how they want to attach to our hardware, and in a ZOS context, you don't see anything in our publications that refers to this mode. You don't see configuration options, again, because we typically in ZOS COM Server support Layer 3 only. And this is what this presentation is going to be about. So we don't describe the other modes. So here I'm discussing a system concept versus just what ZOS supports itself. And bullet 4 there is when you do use Layer 3 mode, we get assist from the hardware. And this is important for OSA. So OSA provides IP assist for things like ARP, checksum, segmentation, etc. And that's very important to our ZOS clients. And so IP assists are not supported in Layer 2 mode. They're not applicable. And they're not supported by HiperSockets at all. They're, again, not applicable. So Layer 3 assists is an OSA concept when you're in Layer 3 mode. When you're in Layer 2 mode, the hardware simply just passes frames without any other assist or processing. Now, mixing these modes. So can operating systems share adapters, a HiperSockets chiplet, or OSA and mix? So let's take the OSA case first. So when different LPARs share an OSA port, they can connect in any mode. They can also loop back and communicate with each other without going over the LAN. And so their mode is, they can use either mode, and OSA will translate the packet from a layer 2 frame to the layer 3 IP architecture. And so the administrators do not need to be concerned with what mode they're configured in. Now HiperSockets is different. HiperSockets, you can still share the same IQD chiplet, but if you are in layer 2 mode, you can only communicate with peer hosts that are using that same chiplet that are also in layer 2 mode. And it's the same for layer 3. So layer 3 can only communicate with layer 3 hosts using HiperSockets, so you can't mix them in terms of having the firmware translate the frames and forward it to the other host using a different mode. I have a figure showing that in just a moment, but this is pretty important concepts, and this is what we're talking about. Page 5 is just illustrating the concepts architecturally in terms of layer 3 is a datagram. It's basically an IP packet, and this is what the firmware processes, an IP header, and forwards and switches packets based on that. Whereas in layer 2 mode, software builds an IEEE standard packet, puts it on the wire, and the wire may be internal. For example, OSA could send it back to another LPAR based on the target MAC address. So there the hardware is just acting as a pass-through without any assistance in processing. And of course, there's a VLAN tagged frame, then that's also in the MAC header as well. So again, layer 3, we're just dealing with datagrams with no media header. Layer 2 mode, software processes all of the media header processing for adding and removing MAC headers, and that's basically the difference for the internal processing as you see here. Now in chart 6, I'm just illustrating these LPARs that are sharing one OSA, and I'm just showing here that they're connected using different modes, and that's okay. It may not be readily apparent, and it's not necessary. But if I do, I show an example here where logical partition 4 and logical partition N are actually connected to the same OSA using different transport modes. And OSA can allow them to loop back and communicate, share the same OSA internally. That works fine. They're in different transport modes, but OSA will translate those packets and forward it just fine. This is supported for OSA. Now on chart 7, I show an example of mixing the same HiperSockets channel chiplet and mixing layer 2 modes. So this same LPARs can only communicate with LPARs that are using the same transport mode. So my layer 2 users are isolated from my layer 3 users. Some customers stumble across this accidentally, others understand this, and this is really the heart of what we'll be talking about today, is the fact that the 2 modes are incompatible. Now, why doesn't HiperSockets translate the frames and allow this to work? Because it would remove the value point of HiperSockets. HiperSockets does not process individual frames. It's a memory-to-memory move, and for the optimization value point of HiperSockets, we would rather not have them process individual packets. It would basically slow that processing down tremendously. So they have to be light modes on HiperSockets to communicate. On chart 8 is a little bit about what ZOS supports. Now, what does this mean for ZOS and this HiperSockets transport mode? So ZOS supports layer 3 mode only, both for OSA and HiperSockets. Now, I have an exception flag there. There's a couple of odd exceptions, and we won't talk about that. But for the most part, you can see the notes I have some notes pages, and I have some notes that are on the actual screen. But for the most part, you won't go in our publications and find us talking about this topic or providing any product externals to display it, because it's basically ZOS is in layer 3 mode. And when we need the IP assist from OSA, and they're very valuable to our customers, and so the layer 3 mode is the most meaningful to our environment. Now, although ZOS only supports layer 3 mode, ZOS also supports a hybrid mode. Now this bullet 2 here I really didn't want to talk about, but in Truth in Advertising I thought it was important that I mention this, that even though we use layer 3 mode only, we do have a virtual MAC address, and our packets can be forwarded by that VMAC, and we can get IP assist in this mode. So we are in layer 3 mode, but we also have the ability, as most of you know, to use a virtual MAC per IP interface. So that provides kind of a hybrid mode, and we recommend this mode. So for any customer that doesn't have a VMAC configured on their OSA interface statement, I would recommend that you review that because that provides significant value for many reasons, and it's beyond the scope of this discussion, but I would encourage you to take a look at that. Layer 2 mode is actually more beneficial and applicable to virtualization when you're talking about Linux guests, possibly having many of them. And again, why you would use Layer 2 mode in a Linux environment is beyond the scope of this discussion, but I provided a couple references there for you to go review that. And again, most of you may be familiar with this information already, but just in case, you can look at the ZVM connectivity book or the Linux device driver. There's a couple of places you can go read about the choices and pros and cons. Now, when combining ZOS and Linux guests that are in Layer 2 mode on the same HiperSockets network, this is where we have connectivity or complexity issues that occur. And this is at the heart of what this requirement and the solution is about. And this is what we're trying to solve with this solution. Now, another background topic. So that was transport mode, Layer 2 versus Layer 3, and that's relative to inside of System Z, our attachment architecture to our hardware. Now, the second topic is just networking 101 background. Most of you may find this very trivial, but it's going to be important because we're going to use these same terms today. So what is a network? What's a broadcast domain? What's a LAN segment? So again, this is just a reminder that a broadcast domain is a network where I can reach every station or computer node on a network using Layer 2 protocol, basically broadcast, multicast, unicast. And you can connect LAN segments with different technology. One of them is a bridge. And so a Layer 2 bridge is certainly different than just a trunk port. Trunk ports basically is part of the LAN. Layer 2 bridge actually spans LAN segments. And what it propagates across there and how it treats spanning tree protocol is different for a bridge port. But in this example, I'm showing that LAN segment 1 and LAN segment 2 are just connected using a bridge technology, which makes it look like one large broadcast domain. Now, that broadcast domain terminates at the IP router. In this example, I can get to another LAN segment, a broadcast domain 2, using Layer 3 protocols to route across this. And so in this terminology, a broadcast domain is actually a physical network. I can reach all my peers by using Layer 2 protocols on a direct network. And so what you'll see us use often in our publications is we'll refer to a broadcast domain as a physical network or a physical network identifier that you can define for some of our ZOS configuration that helps us identify what physical network you're attaching our host adapters to. So again, broadcast domain LAN segments are provided here as background, and just know that a broadcast domain essentially represents a physical network. Now, relative to bridges in broadcast domains, ZVM provides a way to bridge from one network to another, just as I showed you in the previous chart. And in this example here, ZVM is shipped to support several years ago, but we're going to talk about how ZOS is going to be compatible now with the bridge environment. But here you'll show a ZVM LPAR A, and it has a virtual switch, and that virtual switch has a bridge port, which it will now take the network that's known as HiperSockets, an internal LAN in System Z, and you'll see the virtual guest in this round elliptic bubble here that basically shows that they're using something called QDIO-SYS, also referred to as QEBSM. Those guests are attached directly to HiperSockets, and they are bridged through the virtual switch to the external LAN. And to the guests, the bridge is, of course, transparent to them, just as they would be on the previous chart, but they bridge the HiperSockets network to the outside world transparently to the guests. And then we show a couple guests that are actually deployed on top of the virtual switch, and those are for guests that primarily talk to the outside world, and the guests that are deployed directly to HiperSockets would have a need to communicate with ZOS. And so that would be the more optimal configuration for that environment. So you have a couple of choices here, but this bridge port allows the virtual machines to communicate internally and externally, and that of course is transparent to them. And architecturally, it's bridging one LAN segment to another to make it look like a single broadcast domain. And so that basically ties our concepts together. This is support that's existed for quite some time, and ZOS has not been compatible with it. And so one final important concept is that if you're maintaining many virtual servers On chart 11, we talk a little bit about this notion of single versus a multi-home guest. And so ideally, in this case where you're hosting many virtual guests, it's ideal if you can just keep it to a single homed virtual machine. When you start adding multiple interfaces, your complexity rises significantly, and complexity equals cost, and along with other issues. So many of our users really would like to have a single interface into the guest, and it reduces their operation and their administrative costs in terms of doing that. Just as on the previous picture I showed you, where all those guests, if you'll notice, had one IP interface, and they can get to internal peer hosts, or they can communicate with external hosts as well. So single-homed virtual machines is very important to our community that has to host many virtual machines. So that's in terms of a usability issue. So what are the issues we're trying to solve here? So issue number one is ZOS did not support layer 2. So we've already explained how layer 2 and layer 3 users cannot share the same HiperSockets chiplet, and the ZVM bridge environment requires layer 2. So if you want to use or deploy the VSwitch bridge, you would require a HiperSockets channel that's defined with the users must all be in layer 2 mode. So again, customers would configure their environment just as the ZVM switch as I just showed you, but then they would realize they could not connect to ZOS. That's problem number one, incompatibility. ZOS is incompatibility with that environment. Problem number two is just a ZOS only issue. It's HiperSockets usability. So we've had some usability concerns with the fact that ZOS users, when they move LPARs from one CPC to another, that they have to stop and either reconfigure their HiperSockets network in the new CPC, and that would create mobility or usability issues. We do have users that frequently move around their ZOS instances for various reasons, and that's created usability issues for them. You can solve this with different approaches, but with each solution it just adds complexity. So we're going to talk about the ZVM issue and the ZOS only issue. Okay, so let's look at the ZVM first. So here on chart 13 we show the VM environment again with the vSwitch. We have servers C and D that are deployed using native devices, and servers E and F in the VM LPAR that are deployed using simulated devices, in this case the vSwitch. And so what you see here is that the server D we want to focus on just for purposes of this discussion. So server D is again deployed on HiperSockets. It's using layer 2 mode. It has access to any guest that can communicate on this HiperSockets channel, and to any guest that is either on the vSwitch or on the external LAN. So for all practical purposes, LinuxD can communicate with anything, and that's the environment that we're trying to be compatible with. And this environment again requires layer 2 mode only. Now when you look at page 14, it shows how server D could communicate with ZOS. If ZOS was, for example, the database DB2, and server D was providing some type of 2 or 3 tier solution, possibly WebSphere or what have you, it would provide a solution by just simply providing another interface. In this example, interface B, which happens to be another HiperSockets channel, and it's using layer 3 mode back to ZOS. So customers realize this has been the workaround or the solution for years, and that's just not so bad. Of course, it looks pretty obvious, except what if server D you have a need to have 30 of those or 60 or maybe a couple hundred of them? And this issue about multi-home versus single-home IP addresses starts adding complexity for these administrators, and that's the problem. They'd really like to get that back to single-homed guest virtual machine again, and that's been the incompatibility. And so what we're trying to do is introduce this new solution here on chart 15. We'll talk about HiperSockets Converged Interface, and this is a really very high-level illustration of what the solution is, and we'll talk about it in more detail. But the two important concepts before we go any farther is important for you to understand. Number one, what it does is basically HiperSockets transparently converge with your OSA interface. So basically you just configure and use OSA and you transparently get HiperSockets. So that's concept number one. Concept number two, when you do this, your IQDC channel your internal network is logically joined with your external network. So now they become one broadcast domain. In this ZOS only picture that I show here, there's no bridge. The converged architecture that we have in ZOS, we don't forward packets back and forth across the black and red lines like a bridge might. They converge there, but they become one network at that point. And so basically with this solution, you get HiperSockets and OSA by simply just using OSA. And we'll talk about how that's done. But two concepts. They logically are treated as one interface and logically treated as if there's one network. And so how do we do this? So chart 16 is very busy. I apologize for this, but it breaks down the details. So a little bit lower level view of it. Again, this solution's been announced in the 2.3 RFA already, and the announcement was geared towards a first quarter 2018 availability date. And so we plan to make this available at the end of March. And this solution basically provides, again, this convergence of these two technologies to be treated as one. So again, I will not go through all the notes on this page. I'll let you read this on your own, but we have one parameter in ComServer. It's called auto IQD, automatically converge my IQD channels with OSA, and they'll be converged when they're PNET IDs. When you tell us you're on the same broadcast domain, the same physical network, and you tell us to converge them, we will do so. And on the HiperSocket side, we'll use Layer 2 protocol. On OSA side, we'll use Layer 3 protocol, and it'll all look like one. There will be one IP address, one interface. The software above only sees OSA. Everything only sees OSA, OSA MTUs, OSA VLANs. HiperSockets is used transparently. And that network now, PNET A, looks like a single network. Logically, it's one broadcast domain now. That's not bridged in a ZOS environment, but logically it is joined together. So that's HiperSockets Converged Interface. Again, there's several details here, and we'll talk about more of them as we go along. But the concept is you just start, operate, monitor, use OSA, and you get HiperSockets along with it for free. Chart 17, the next chart provides some of the highlights. Again, I don't know that I need to go through every one of them, but again, the upper layers only see an IP interface that is in fact OSA. All the attributes of your OSA interface are exposed to the software. So, for example, like the IP route and the MTU. The HiperSockets Layer 2 path is used by the lower layers of software of the stack when the peer host is found to be on that IQD network. So basically, we'll dynamically discover that a peer is actually inside the machine, and we'll use the internal path. And so both IPv4 and IPv6 are supported for this, and HiperSockets Converged Interface inherits the OSA's interface attributes. Its IP address, it actually reuses its virtual MAC, its VLAN, and MTU. And VLAN, of course, is optional. All HiperSockets related artifacts, resources are dynamically created, and here I provide the dynamic naming convention, so you can display the HiperSockets Converged Interface or operate it if you want to. It's not necessary to operate it because it will follow your OSA behavior, but there are the names that we will build dynamically when we create this. Layer 2 architecture requires that software transmits and receives frames now. So on the Layer 2 side, on the HiperSocket side, we're exchanging frames, and we're also taking responsibility for Layer 2 protocols like ARP and neighbor discovery, which is now done in software. And the ZOS has something called Accelerator, where we can forward packets in an efficient manner. This is also supported. There's a little bit more detail about how that's supported in the backup charts. An auto IQDC setting can be changed on the fly by using VarioBay. So that's just quickly the highlights. Chart 18 talks about how you get this support. Those are the two APARs that will have PTFs very soon. They will co-rec each other, and they will shoot the ship at the end of the month. Again, there's a reference to the announcement letter if you'd like to go review that. Again, when this function is available, it will be off by default. You'd have to enable it. Again, terminology throughout our publications and in this presentation, you'll see things that refer to HiperSockets Converged Interface or IQDC. There might be some displays that display it either way. IQDC is the control or the way that you manage the function on and off. HiperSockets Converged Interface is the actual solution, but sometimes we'll refer to either acronym, which is the same solution. Now, there are no software or systems hardware requirements or codependencies. All the support that we need for using the bridge and the HiperSockets firmware is all in place already, and so there's no requirements to apply the ZOS software and turn the function on. So now let's look at the solution. Now, when you apply the solution to the problem we first described, now server D can use one IP interface to access HiperSockets, and they can now access anything, even ZOS. Stubborn ZOS finally comes along and provides layer 2 support, and now you've got one interface in server A, and you have OSA and HiperSockets connectivity. Now, there's a couple important concepts here about the solution, and this is one that everyone is going to misunderstand. I'm going to say it here, but you're still not going to understand it because I have a difficult time conveying this. But our support does not support the VM bridge. Our packets do not go through the bridge, but we are now compatible with the HiperSockets channel that connects to it. So that's in the bubble on the left. That's a lot of words to say we're now compatible. We can connect to server D, but we use OSA for external communication. So we go up to the bridge but not through it. And then on the bubble on the right, it basically says that the solution is provided by ZOS. Server D doesn't change anything. It's just how it's configured. And server D can now communicate with, finally reach ZOS and reach the outside world or servers that are deployed on the vSwitch using a single IP interface. So from a usability standpoint, this finally connects the dots, makes for a very nice System Z solution that works for all configurations. So the HiperSockets Converged Interface solves the incompatibility with the VM bridge. So we're switching topics now. We'll momentarily forget about the ZVM bridge environment. So what does this mean for ZOS only customers? Do they need to pay attention? Does it help me at all? Let's talk about that. So moving ZOS images around can be an issue. So on chart 21, this is where I think it really starts helps illustrate the value of this. So imagine a simple environment, 2 CPCs, maybe it's the same sysplex. I call them sysplex A here. Don't put too much into that, but I'm just trying to get a very vanilla example. The 3 LPARs in each CAC, and they all connect to the same LAN, and they connect to HiperSockets internally. Now, so most of you will realize that there are 3 networks here. There's the external LAN. There are 2 internal networks. There's network X, network Y, and network A. And so the host in system A, of course, are configured to connect to network A and network X. And here I call it also IP address A dot something and IP address X dot something. And then if you look at like server D on the right, it connects to the external network A.4 and another unique internal network Y dot something. So I have X, Y, and Z, 3 networks, a very simple configuration. And this is, so every LPAR has 2 IP interfaces, IP routes, all the attributes you need to maintain them, all the administrative overhead of maintaining 2 interfaces per LPAR, 3 networks for the administrator of these 2 systems. So this is the way it works today. And so now if I look at this, what happens on the next chart on 22, what if I move server C over to CPC Y? Well, obviously over there now I still want HiperSockets. So if I do, I just simply reconfigure that to use the other internal interface subnet Y and VLAN Y in this example. So the administrator either had to use system symbolics to substitute that IP address, which you can do, or you can just reconfigure it, or you can use some type of scripting to reconfigure that IP interface to address that unique internal network in the other system. And that doesn't seem so bad unless you're doing this daily. And what we found is customers struggled with this notion that, yeah, HiperSockets is great, but when I move my systems around, I have to stop and do something, and that creates some usability issues for our users. And so what this solution does here is you'll see on, let's look at chart 23 now. Now the chart 23, contrasting with 21, if you have the ability to look at both of them, it's really very powerful to illustrate this. So now all those systems, those LPARs, went from 2 IP interfaces to 1. Now they're only configured with OSA only. they're all configured with IP subnet A. So the X and Y's are now gone. And so they configure OSA, HiperSockets is converged transparently, and the HiperSockets network on system on the left is now network A, and the one on the right is also network A, and they are, even though they appear to be discontiguous, they're all one network because all the systems that are using it are using a converged interface, and they can now use a single IP interface to address a single network. So broadcast domains on this picture now, I have one. Physical network, I have one. OSA is called PNET A, and these internal channels are also called physical network A, one broadcast domain. I went from 3 to 1, so very powerful. You can imagine this if you had dozens of LPARs, it can be quite beneficial in terms of overall usability of HiperSockets. So now you don't configure it, see it, touch it, operate it, you just operate an OSA. And now on chart 24, I illustrate moving server C over to the other LPAR, or I'm sorry, the other CPC, and now there are no operational changes because you don't configure HiperSockets, so I don't stop and reconfigure my IP interface for HiperSockets. It's simply transparent, and I'm just connecting to A when I move over there. And so operationally, it's now very easy to provide mobility for ZOS instances. And so it's just not the mobility thing, it's the entire overall general usability that this improves in terms of number of interfaces that you're managing and what you have to worry about in terms of managing an internal network. So you can see how HiperSockets Converged Interface helps this environment as well. So I have a couple more charts. I'm going to turn it over to Randy, and this one on chart 25 is a little bit messy, but I wanted to make a couple of points here. What about multiple OSAs? So I haven't addressed that yet. So I just provide a couple examples just to make a point or two here. So in this example, I say I have multiple OSAs, but perhaps I don't configure VLANs. It all looks like one subnet. But the point is that for every OSA, if you turn on auto IQDC, every OSA that's configured with PNET A says you're all going to the same physical network. Well, then I will converge all of you. So all the OSAs get the converged interface. It just happens that we use one channel, one device. So the first OSA that starts will activate it, and the other ones will use it as well. So they're all of them on the same physical network will use the same device, and the last OSA that terminates will terminate the HiperSockets device. But basically, as you add OSAs, they all use a single internal interface. And the next example in chart 26 provides the same one, but in this one, now the interfaces are configured with a VLAN. Here's another high availability typical configuration, but now they use different subnets, and they use dynamic routing for failover. But nevertheless, again, all the OSAs that have a matching PNET ID that matches their HiperSockets physical network ID, and you've turned on auto IQDC, will converge all your OSAs, so they'll all have access to this converged HiperSockets interface. We just use a single HiperSockets device. From a resource standpoint, it's a very efficient model. So they all use the same device, and that's really the point I wanted to make. Chart 27 is a refresher for PNET IDs. I've been using that term, physical network IDs, and how HiperSockets Converged Interface affects it. Now, most of you on this, I'm hoping, are familiar with how we use physical network identifiers. It identifies a physical network and broadcast domain, which we know is the same. It's configured in HCD, and for OSA, it's on a port basis, or for Rocky, it's a physical port attribute. Where does this port connect? What physical network does it connect to? And all the operating systems and the hypervisors, what have you, can dynamically learn this value by configuring it in one place. HiperSockets Converged Interface changes the rules a bit because we now logically combine networks. And so for SMCR, we use PNET IDs to associate OSAs with Rocky ports. And for SMCD, we use this PNET ID to associate OSAs with ISM ports, our logical port, or HiperSockets with ISM. Alternatively, you can use one or the other. But without HiperSockets Converged Interface, HiperSockets and OSAs can't possibly be the same physical network. However, this function changes that rule that I described there with bullets 1 and 2. When you get to bullet 3, HiperSockets Converged Interface is a bit of a game changer because it now associates OSA with HiperSockets. So what's new with the Converged Interface, your OSA and HiperSocket networks are now the same. They have the same name. So look at chart 21 when you look at this bullet 3, and then see what happens with HiperSockets Converged Interface on chart 23. Contrast the two of them, and now you'll see OSA and HiperSockets must have the same PNET ID in order to use the converged thing, and look to see how it changes for your users that possibly are already using PNET IDs for using SMCR or SMCD. So now all three functions have a dependency on this notion of PNET IDs. So that's a lot of information on page 27. I realize that, but I think if you look at the charts and look at these points made here, it will make sense to you. Now, chart 28 says, well, what if I had PNET IDs and I want to use HiperSockets Converged Interface with SMCD? So here I provide some, just a little bit more information, again, from the previous chart about how HiperSockets Converged Interface changes this. Again, refer back to chart 21. Again, without this HiperSockets Converged Interface, ISM can be used with OSA or HiperSockets. But it's not possible to be associated with both because they're independent physical networks. But with HiperSockets Converged Interface, they are now the same network, so that changes it. And if you read down the progression, it's kind of a hierarchy of how the rules impact that. But just know that HiperSockets Converged Interfaces combines the networks, which combines their PNET ID into a single network. And so, again, a lot of information about how PNET IDs affect the different functions that depend on it, and it's too much information for this presentation to talk about the SMC aspects, but if you're using it already, I would encourage you to take a look at that. Okay, so at this point in time, that's the background information. I'm going to turn it over to Randy to talk about how this affects ZOS, some displays, and some configuration information, and everyone should be on chart 29 now.
All right, thanks, Jerry. So at this point, we're going to go through product externals. Jerry already alluded to that we configure the new functionality of HSCI with a single parameter on the global config in the profile statement called auto IQDC. If you enable this, if you specify the new parameter, then you'll allow the COM server to automatically create and converge IQD devices or interfaces with the associated OSD interfaces with matching PNET IDs. Be aware that the default for this new function is disabled. The no auto IQDC is the default. The auto IQDC parameter has one subparameter, and by default, if you specify auto IQDC, it's called all traffic. It means that all traffic is eligible to flow over HiperSockets in this configuration. We also offer a no large data subparameter, and what that means is if you have streaming socket applications that send 32K or larger frames, then they would opt out of using HiperSockets, and those flows would go back over the OSA interface, and that's just for CPU considerations. Moving on to some HCD configuration requirements. We'll see a panel and a few foils, but when you're configuring the IQD parameters, the chiplet parameters, you'll have to specify an external bridge, and that's basically how you specify you want HiperSockets configured, the chiplet configured in layer 2 only mode. And on that same panel, you'll also specify a PNET ID, and preferably it will match your OSAs if you want this to work correctly. So, moving on, the IQDC interface is dynamically built automatically. Basically, when the first OSD interface with a PNET is activated, VTAM will go out and look at all the chiplets that look like they're defined with external bridge and that has a matching PNET ID of the OSA, and VTAM will dynamically build a TRLE on the fly for you and allocate. It will try to allocate 2 control channels and 8 data device channels to support up to 8 stacks to use this. And then when VTAM learns that information, it passes it back to the stack. The stack realizes that VTAM found the correct chiplet, IQD chiplet, passes that information, the chiplet ID back. It finishes building a dynamic interface on the stack, and the stack kicks off an activation request to VTAM to dynamically start that. And then on the reverse side, when the HiperSockets interface will stay active as long as you have at least one OSD interface of that same PNET active. And when the last interface is stopped by an operator, then VTAM will automatically deactivate the HiperSockets interface as well. I do want to point out that the dynamic TRLEs, normally TRLEs are for life, but we made these kind of to support dynamic I/O. So if you have a misconfiguration or if you want to change the channel IDs, when the last OSD interface is taken down, and basically the last data device for the IQD chip, it goes away on the TRLE. Eventually, about 60 seconds to 90 seconds later, the control channels time out, and VTAM will dynamically delete the TRLE, and it will be rebuilt. So if you need to change dynamically the channels or chiplet IDs for the IQD channels for your HiperSockets Converged Interface, you can do so, and VTAM will relearn them next activation of the OSD. All right, so we did enhance to support the new function, various Netstat displays, and when you display your OSA interfaces now, you'll see the associated HiperSockets. And since HiperSockets is a dynamic interface, you can also display that through Netstat Devlinks, and we'll see a couple of examples coming up on a few foils later. This is an automatic function, so the operator does not have to operate the IQD interface, but you may choose to do so. So you can stop it and start it at will. But if you do stop it, VTAM or a comm server will not automatically restart it when you activate an OSA. You would have to manually restart it if you're going to take the controls of it that way. The IQDC interface only supports unicast, except in the cases of when we're supporting ARP and neighbor discovery flows, and the multicast and broadcast is used in that aspect. But otherwise, comm server uses OSA to provide necessary multicast and broadcast support. And just to touch on network management, we did update the NMI and SMF, SNMP, and for dump analysis, TCP/IP/CS to support various details in that. We'll go into each of those on the next few foils. All right, moving to slide 30. Moving into HSC, as we spoke about in the TCP/IP profile, simply just an auto IQDC parameter. And the second piece is on number 2 bullet under the TCP/IP profile, for the OSA's interfaces, we require that you code interface statements. So if you code device links and you want to take advantage of this function, you'd have to convert those to interface statements to be eligible for this function. If you did activate it and you coded a PNET, it would probably allow it, but it wouldn't work. It would just silently not have an associated interface, and you'd scratch your head trying to figure out why not. And the other requirement in your profile is that the OSD interface statements must have a VMAX specified, and not just any VMAX, an OSA-generated VMAX. So we do not accept user-defined VMAX for this support. So it's just to guarantee that we have unique VMAX, since we're going to be reusing them on the internal network as well as the external LAN. VLANs are supported, but they are optional. And if you do code them on your OSDs, we certainly register them on the HiperSockets interface as well. All right, so moving along to HCD. So when you're defining your IQD chiplets, you must have and we're going to see a foil on this later, but you must specify PNET, and the PNET ID must match your OSDs, and it must be externally bridged type of chiplet. When you're configuring this, as I said, minimally we need, if you only have a single stack, then minimally we need 2 control channels and a single data device to support one stack, and then we need 1 data device for each additional stack, so they'll be using this same the same IQD chiplet. The default when you're specifying IQD interfaces in HCD is you get a 16K frame size. We do recommend that you bump that up to 24K frame size for various reasons. One's for performance, and another one, it basically optimizes things. If you're using Ethernet jumbo frames, if you don't bump it up to the 24K frame size, then some of the Ethernet jumbo frames cannot go across that, and they would opt to, basically, if you code 16K or take the default, a jumbo frame cannot be sent across the HiperSockets in that case, and that's why we're recommending you bump it up to 24K. And the last bullet on this right under HCD is the OSD chipbits must have a PNET ID that matches your IQD chipbit configuration. And if you're already using shared memory communications and your OSDs already have that, you can certainly just propagate the same PNET ID into your HiperSockets Converged Interface plan. All right, moving on to slide 31. This just shows an example of the HCD screen that you'll see for configuring your IQD parameters. The first is it'll default to 16K as the maximum frame size, but we're recommending you code 24, but that's optional. The next two parameters are required. So for the IQD function, you must specify option 3, which is the external bridge function, which allows it to operate in layer 2 mode. And the last bullet is the physical network ID. In this case, it's specified as net A, and that must match your OSD channels or interfaces that you're associating with. All right, moving on to slide 32. This is just the global config auto IQDC parameter that we touched on. Just kind of shows you the railroad track view of it, and I will point out that the default is disabled, no auto IQDC. And if you want this functionality, you must specify it. All right, so moving into page 33, we're going into some of the Netstat changes. The first being the Netstat config. That simply shows you the auto IQDC value that you specified, something to verify if you're not seeing things set up correctly. And I will point out, don't be confused with the auto IQDX, and that's something that Jerry touched on with the IEDN solution. So that is a separate function that has no relevance here. So auto IQDC is what we need for this function. All right, page 34, moving on to the Netstat Devlinks updates for the QDIO interface display. So on this foil here, there's absolutely no changes, but I'm going to move to slide 34 and it shows a continuation of that. You'll notice under the interface statistics, there's not a lot going on under this OSA. It just shows one outbound packet being sent. And that's basically, that will show you all, as you are familiar with, all the in and out bytes and packet counts for that data going over the OSA. But you'll notice at the bottom of the screen, you'll see the associated IQD or HiperSockets Converged Interface. And in this case, it's EZA IQC EZ0. And it shows that that device is ready. And it shows you the number of packets that were basically diverted and sent out and received over this HiperSockets channel on behalf of this OSA interface. All right, so that's good information. So if you're seeing not enough data going up, what you expect to see is most of the traffic going over HiperSockets unless it's not eligible for whatever reason. And we'll get to some of that in the diagnostics section. And one of the cases, like one of our testers, when he was taking a default of the 16K maximum frame size on his HiperSockets, and he was using jumbo frames on his Ethernet, and most of the traffic was going over the OSA, and that was one reason why. All right, moving on to slide 36. This is just a Netstat Devlinks display of the HiperSockets Converged Interface itself. You'll notice the new name, EZA IQC, and it ends in the chiplet ID of the device, the HiperSockets chiplet. It has a new interface type of IPA-Q IQDC. That's a mouthful. On that same display, we do associate the TRLE name that VTAM dynamically built on our behalf, and that's it. So one thing to put onto this, so when we display the HiperSockets interface itself, the converged interface itself, under the interface statistics, this represents all the traffic, all the inbound byte counts, all the inbound unicast packets that were received on behalf of all the OSAs behind it. And the same thing goes on the outbound. So, and the outbound represents all the data that was diverted from your OSAs over this HiperSockets interface. It's a culmination of all of it. Versus the one that was on the OSA specific, that was just the byte counts that was sent over the HiperSockets on behalf of that specific OSA. That's kind of a key point to remember. All right, slide 37. Hopefully you won't need to use these. These are more, this is like a Netstat ARP display. This is what I would point you to look at if things aren't working well or you're seeing all your traffic go over OSA. This would be a key place to start. So if you use an IPv4 interfaces, you would what you want to see here is if your remote IP address shows up here, that means it's resolved and that's good. If you display the ARP cache entries and you don't see your target IP address, that's probably a bad thing. We'd have to understand why that isn't being resolved. Is the frames being dropped or whatever? But if it's not displayable here, then that's a cause for concern that we'd have to get to the root cause of that. So in this case, the remote IP address of 172.16.1.5, that's resolved, and it's reachable over our local interface, EZA, IQC, EZ0, and then it shows you the MAC address of that local, of the remote link that we're sending it to. The very bottom interface, the 172.16.1.3, that is a local home IP address cache entry for our local interface. All right, moving on to slide 38. This is basically the same thing, except it's a neighbor discovery flows for the IPv6 configurations. So basically these show what you're looking for on this one is the remote IP, the target address to be in a reachable state. If you're not reachable, then it's basically that's reason for concern why you wouldn't be using the converged interface, and we want to be using it. So these are just some things to look at when if you see things aren't setting up right or as expected. One thing to point out for both ARP and neighbor discovery, we do have 5-minute timeouts. So occasionally we'll refresh these to make sure things are still reachable over these interfaces and MAC addresses. All right, moving on to slide 39. On the VTAM side of things, this is the dynamic TRLE that was built. Jerry on a previous foil gave you the name, so this is an IPv4 configuration. Things to point out, an existing message for IQDC, the 2337I message shows you the chiplet type of IQD, shows you the chiplet name, and it shows you the associated PNET with this HiperSockets channels. A little redundant is message IST2319I. I want to point out this had another name. It was called IQD Network ID. And our tester thought that was confusing, a little confusing name since it's really the P-chip, if you will, or chiplet ID of the HiperSockets interface. So we renamed that to be physical channel ID to kind of match HCD to remove the confusion between the PNET ID. All right, and if you notice the two control channels in this one, you'll see the read control channel is EZ0 Charlie, followed by the write, the EZ0 dog, and there's one in this display. It just shows one stack using the data device EZ0 EZ, and that stack is TCP/CS1. And we do link the interface name, the dynamic interface name that the stack is using to connect to this device. And presumably there could be 7 data devices behind this and being used simultaneously by other stacks in the same LPAR. All right, moving on to slide 40. This just shows I'm not sure everybody's familiar with this. This is a command that came out a few years ago when shared memory first came out. It's basically a Devlinks command with a PNET ID flavor. This is PNET ID specific, meaning you can say PNET ID equals, in this case, ZOSNet. There is in the backup charts, there's a display example that shows PNET ID equals asterisk, and it basically groups the interfaces that are all by PNET ID, and it just shows you the interfaces from each set of PNET IDs. This one being specific of ZOSNet, it gives you a little bit more information. In the PNET unspecific with the asterisk, it only shows you the interface name and interface type. But if you want to drill down and get a little bit more details, then specify the PNET ID that you're interested in. So in this case, there's only 2 interfaces with the ZOSNet PNET ID configured in this stack, and it's a QDIO 4103, and the interface, the converged interface, EZA IQC E0. And the little speaker note right there just is pointing out that we notice that we do not specify the VLAN or the VMAC underneath the HiperSockets interface. And we went round and round on this but if you imagine if you had 4 or 5 OSs all with the same PNET and they converged into this single HiperSockets, we don't want that. It seemed redundant to say list all the VLANs and VMACs when you just know that they're all associated if they're under this display. So just know that the QDIO, VLAN, and VMACs are registered with the HiperSockets interface. They're just not displayed. All right, on slide 41, moving into the network management product externals. We did update NMI and SMF and SNMP to basically update it to the various Netstat display changes that we to support. So for the get profile under NMI, we show the new auto IQDC parameter and the subparameters. The get IFs call, it now shows you the associated IQD interface name with the OSA. And if the dynamic IQD interface is also displayed as a separate record since it is an interface. The GetIF stats was updated to show basically bytes and packet counts for interfaces that were diverted to use IQDC, just like the Netstat display. The dynamic IQDC interface is also displayed as one of these interfaces in this output. The GetIF stats extended is updated to show the IQDC interface and the associated data device that is being used by that stack. Now moving on to SMF, we basically reswizzle that and provide the same information. So the TCP/IP profile event record subtype 4 was updated to reflect the new global config parameters, meaning the auto IQDC. The interface statistics record subtype 6 was updated to return information about the IQDC interface, similar to what was provided for layer 3 HiperSockets interfaces. The OSD interfaces will now contain the associated IQDC interface that is being used, basically provide the unicast inbound and outbound byte counts that were diverted over the IQDC interface. In the speaker notes, you can see more about the TCP/IP, PCS, and SNMP updates, but we're just going to skip those since there's pretty much redundant information at this point. All right, moving on to slide 42. Diagnosis, what IQDC interface does not activate, so what do? So if you drill down and start with your HCD configuration, since that's where it all began. So the IQD chiplet, was it defined with the external bridge? If it was not, VTAM, even if you coded auto IQDC, it won't find the chiplet because we're specifically targeting chiplets that have a PNET that matches your OSA and it has that external bridge function, which means it supports layer 2 mode. I touched on the second bullet about the PNET IDs must match. And if you look there, it says, see the backup charts. In the backup charts, there's some really good commands, for ZOS commands, that allow you to display the chiplets or the PFIDs in your systems to show what the operating system thinks you coded for PNET ID. So you may think you coded one thing, but maybe the HCD, the IOCDS didn't take effect, but that'll show you what is active in the system. So I urge you to take a look at those because that's a key stumbling point. All right, more on HCD. Verify that you have defined enough channels. We recommend 10 and the devices are online. That's another thing. So VTAM doesn't, when he's dynamically provisioning or building these TRLEs, he's just looking for the right type of device and right PNET. If it's not online, that doesn't prevent him from building the TRLE. But when we go to kick off the activation, it will fail if it's not online. And I did have a tester trip over that. So verify your IQDC channels are configured online. And just as a starting point, if things aren't working well, issue the display of the VTAM TRLE, the IST TRL command, or DNet TRL, just to see, did we build one of these HiperSockets dynamic TRLEs? That's a key indicator. And is the dynamic interface for the HiperSocket, the converged interface, displayable from the stack's perspective? These are all little clues to kind of help you figure out why it's not working. All right, moving on to your OSA config. Again, we're going to harp on this. Verify the PNETs must match. You can't say that enough. Use the DNet Devlinks PNET ID displays to show you what the stack thinks the PNET IDs, and along with the operating system PNET ID displays. Verify the auto IQDC setting is enabled. It does not default to on. Again, the OSA interfaces must be interfaces, and you must use OSA-generated VMAX. Otherwise, they are not eligible for this solution. There's an activation sequence tip that Jerry added here. Remember, OSA interfaces must be started after your IQD HCD configuration is in place. So your LPAR has to have IQD interfaces or channels displayable and online to that LPAR for us to find them and dynamically build this and kick things off. So if you'd have to do dynamic I/O if you didn't do that in that order, and then restart your OSAs to kick it off again for VTM to dynamically, and the stack to dynamically build the interfaces and learn the IQD interfaces. And there's a little footnote at the bottom that you need minimally 3 channels of the externally bridged data devices and control channels for this solution for a single stack environment, and 1 additional data device for each additional stack if you're using multi-stacks. All right, slide 43. IQDC interface activates but is not being used. And in fact, there could be various reasons. We'll go through those. So verify the peer, and it's on the same host, and HiperSockets is active, and it's using the same IQD chiplet. You're using channels out of the same chit, if you will. And the IQD chiplet is configured with the external bridge parameter. That's key. So a big key on that one, if you if you see a TRLE built, then you know you got the channel right and the PNET matches your OSA. So that's a big step if you got that far. Or maybe you don't have enough data devices if you have multiple stacks, things like that. When Linux is the peer host that we're trying to communicate, verify the Linux is bridge eligible. And for Linux to be bridge eligible, on Z14, it's eligible by default. But if your Linux is executing as a ZVM guest, the guest must be configured with the QDIO assist parameter to be bridge eligible. When ZOS is the peer host that we're communicating with, then ZOS must be configured with IQDC, and that's meaning auto IQDC that we talked about earlier. You have to use standard, the configuration has to use the same subnet for connectivity, and VLANs optionally. They must match. If one side's using a VLAN, the other side must be using the same VLAN. Use your display of the ARP or neighbor discoveries to see, does the stack know about this partner? Does it have an externally resolved neighbor discovery or ARP cache entry that says it's reachable through HiperSockets? And use the reliable ping command. That's a nice little connectivity tool just to verify that you can ping it, and is that data, ping it with enough bytes that you can see, is it taking that path, display your OSA that you think you're pinging, does it go over the HiperSockets, or is it using the OSA? If it's using the OSA, then you'd have to drill down further to figure out why not, and some of the key points was that maximum frame size issue in Ethernet jumbo frames. And that's what the last tip is about. So also remember the no large data. If you specify that, that's another key indicator of why, if you're using large sends, that it would opt to use OSA just for CPU savings. All right, moving on to, this is the last 4 that we're going to present here. Just things to think about. We're on slide 44. Just consider the PNET rules that Jerry talked about earlier with OSA and HiperSockets, how they had to be different in the old days, and now with this new solution, they could be the same, or they must be the same to use the converged interface. And how does that impact SMC usage if you're using SMC? And just reference charts 28 and 29, and there's some backup charts on the PNET ID that I discussed earlier. Bullet 2, a single IQD interface data device is used per PNET ID for all the OSAs with that same PNET ID per stack per IP version. That's a lot in one bullet, but I think it makes sense. So basically, all your OSAs, IPv4 OSAs on a single stack, all use a single HiperSockets interface, and all your IPv6 OSAs use another IQDC interface. So I don't know if we made that clear. We didn't have a display of it, but VTM would dynamically build a TRLE for IPv4 access connectivity, and VTM would dynamically build a TRLE for IPv6 access, as well as the stack would build an interface for IPv4 and a separate interface for IPv6. I highly recommend bullet 3 to review the TCP/IP configuration guide updates that Jerry provided. It is a wealth of knowledge, and that should give you a lot some time for that, because it's quite a large section and quite a lot of information. It encompasses all the information here and probably a little bit more details as well. So I encourage you to review that. All right, bullet 4, the IQDC interface uses each associated OSA's MAC and optionally VLAN. So this is a key design point. So all the OSA's VMAX are registered on the HiperSocket interface during activation. As the interfaces OSA's are deactivated, then we'll deactivate the VMAX from the HiperSockets connectivity, from the HiperSockets configuration, if you will. And just understanding this key design point will help your administrators understand how this is all working behind the scenes. I know a lot of it's automatic, but if knowing a couple key design points kind of helps clarify things in your mind, how things work. Another thing that Jerry mentioned earlier is bullet 5. The upper layers, from a stack perspective, they only see the OSA interface. So everything is pretty much operated from that OSA standpoint. Routing, IP addresses, MTU size, OSA, etc. If you run a packet trace, the packet trace, guess what you run it on? You run it on the OSA interface. And under the covers, we'll give you a display of what on the outbound. On the outbound interface, it always looks like it's taken OSA, even though it could be taken HiperSockets in these cases. But that's kind of a caveat in that the packet trace is cut at a higher layer than when we make the decision to send it over the lower layer HiperSockets if we have internal connectivity. But on the inbound side on a packet trace, we will mark a packet with an IQDC tag or flag that will show that it did arrive over HiperSockets on behalf of this OSA interface. But just want to point out, and there are some examples in the backup charts of packet trace examples. And for migration purposes, when you're implementing IQDC from a ZOS to ZOS solution, then both ZOS instances must be 2.3, since that's the only release that supports this at this point.